In this video, we are going to study initial and final value theorems. So let us start with first initial value theorem. So in case of Laplace transform, this initial value theorem provides us a way to find initial value of a signal. So let us consider a signal x of t whose Laplace transform is given as x of s. Now we are supposed to find out the initial value of this signal. So initial value can be represented as x of 0. Now if we have Laplace transform of this x of t signal, we will have the equation for x of s with us. Now from this x of s, we need to find out initial value. So this initial value theorem provides us a mechanism where we can find out the initial value of any signal in Laplace domain. So we can say that initial value theorem is used to find initial value of signal, that is x of t, in Laplace domain. So this Laplace domain is also called as S domain, and remember here we need not to convert this x of s signal into x of t. We can directly find out the value of x of 0 from x of s. Therefore there is no need to use inverse Laplace transform. Now see, what is the equation for this initial value theorem? So we all know unilateral Laplace transform, which is given as x of s equal to integration 0 to infinity x of t e raised to minus st dt. So we use unilateral Laplace transform for causal signals. Also we have the differentiation property of unilateral Laplace transform. d by dt of x of t is equal to s into x of s minus small x of 0 minus. So this small x of 0 minus is nothing but our initial value of signal x of t in time domain. So this value is initial value of x of t signal. So this is in time domain. Now we are supposed to find out this x of 0 value using the equation for x of s. So let us derive the equation. To find out initial value, so we need to find out initial value of signal x of t. So this initial value can be represented as x of 0, which is equal to, suppose if we represent this equation in time domain, this x of 0 will be equal to limit t tends to 0 x of t. So this equation is in time domain, but our aim is to find out value of x of 0 from x of s, that is Laplace domain. So we need to make use of unilateral Laplace transform as we have the causal signals. So consider an equation. We need to find out Laplace of d by dt of x of t signal. So in this case, its unilateral Laplace transform can be obtained as integration minus, it is not minus, now it is unilateral, so integration from 0 to infinity instead of x, now it is d by dt of x of t with the basis function e raised to minus st dt. Now take Laplace transform on both sides. So here on the left hand side, Laplace transform of d by dt of x of t. So if we go through the differentiation property of unilateral Laplace transform, d by dt of x of t is equal to s into x of s minus x of 0 minus. So let us take the Laplace transform. So our equation becomes, so here d by dt of x of t, it becomes s into x of s minus x of 0 minus, where x of 0 minus is the initial value, is equal to this equation, keep it as it is. Now apply limits on both sides. So limit s tends to infinity. So we get the equation as limit s tends to infinity. In the first left hand side we have s into x of s minus x of 0 minus, and towards right hand side it is limit s tends to infinity, integration of 0 to infinity d by dt of x of t into e raised to minus st dt. Now separate out the limits. So limit s tends to infinity, s into x of s minus limit s tends to infinity, x of 0 minus, equal to, now if we evaluate this limit, so if you look at the right hand side here, s tends to infinity. So if we substitute this value, here we have e raised to minus st. So if we substitute this value, this value of this equation becomes 0. Now here the first term is limit s tends to infinity, s into x of s minus second term is x of 0 minus. So here our limit is with respect to s, and the value x is with, it is of x of 0 minus. So here this limit is excluded, and we get the answer as limit s tends to infinity, s into x of s minus x of 0 minus equal to 0. So just rearrange this equation. We get the initial value x of 0 minus is equal to limit s tends to infinity, s into x of s. So using this equation we can find out the initial value of signal x of t from the Laplace transform of that signal. So this is called as initial value theorem. So just to summarize again, so we have the unilateral Laplace transform, x of s is equal to 0 integration 0 to infinity x of t e raised to minus st dt. We have the differentiation property of unilateral Laplace transform, d by dt of x of t equal to s into x of s minus x of 0 minus, where x of 0 minus is called as initial value. And using initial value theorem we are supposed to find out this initial value. But the advantage of this initial value theorem is we can find out the initial value of signal x of t, which is represented as x of 0 minus or simply x of 0, or in some cases we can represent it as x of 0 plus also. So this x of 0 value is obtained from the equation of its Laplace transform. So if we have signal x of t, its Laplace is x of s. So now I need to find out x of 0. To find out small x of 0, I can make use of x of s, and this derivation is nothing but your initial value theorem. So we have derived this equation by using the differentiation property of unilateral Laplace transform. So we have obtained Laplace of d by dt of x of t. We have simplified the equation, and then we have obtained the answer of initial value theorem as x of 0 minus is equal to limit s tends to infinity, s into x of s.